and if you need something, you just have to ask to Andrea Capelli, which is the other local. Thank you.
Okay, so morning. So the main result we got yesterday was that under very general conditions, alias the theory to be local, to be translation invariance, to be rotation invariance and dilatation invariance, out of this simple assumption, you got that the dilatation, which is a global transformation, get locally. And locally means you have a conformal symmetry. So we say that in generic D dimension, the group is finite, is D plus 1 times D plus 2 divided by 2. And specializing to 2 dimension, it seems that we have a violation of what we just got, namely that the group is finite, simply because in 2 dimension, conformal symmetry, which I remind you are those transformations which rotate locally, stretch it locally, but preserve the angle between 2 vectors, they generate to an infinite number of transformations which are all the complex analytic function. And any complex analytic function can be expanded around point analyticity in Laurent-Cauchy series, and therefore you have an infinite number of parameters. So we comment that this is not actually so, because any analytic function cannot be small everywhere, so somewhere has to really be very violently divergent, and the only transformation which can be small everywhere are essentially the Möbius transformation, which are this one, so the birational mapping one-to-one of the Riemann sphere into the Riemann sphere. Now you might ask, since this theory, these functions are not constant, has to diverge somewhere. Indeed, it diverge. It diverge in z equal minus d over c, but this is a fake divergence, because I can make a change of transformation going around the infinity and redo the stuff again. Okay? Because this is just a Riemann sphere mapped one-to-one into another Riemann sphere. This transformation is an amazing property because, for instance, circular mapped into the circle, including circle also line. Symmetric point with respect to the circle are preserved in the mapping. If the coefficients are integer, this will constitute the so-called modular group, one discontinuous group which has taken the attention of mathematicians for centuries, and this and that. So even though it looks very innocent and very simple function, nevertheless, this class of function is extremely important and got the attention of scientists and mathematicians for many years. So I stressed yesterday that the real symmetry of the theory will be those transformations, and symmetry means the action will be, the variation of the action under this change of coordinate will be 0. So this is a symmetry. These guys are not symmetry of the theory, and we have to know how to deal with that. Now, before moving on, let me just observe that we can associate to this transformation some algebras, and actually infinite dimensional algebras. Now, I told you that is useful to introduce 2 sets of coordinates that the way you introduce, of course, is linear combination with imaginary coefficient, and then it's z and z bar, And of course, as I introduced, this is Z star. But you might take the point of view that X and Y are also complex. In a way, this will be a change of variable to a new variable, and consider Z and Z bar as two independent complex variables separately. So in a way, our space will become C2. And at the end of the day, when we want to really talk about the physical system, then we have to make the identification in which Z bar corresponds to Z. Okay? So for the time being, I'm going to use and justify later, when I derive the word identity, that indeed in this conformal field theory the Z and Z bar part are decoupled, at least algebraically. Physically, they are not decoupled, as we'll discuss later. But for all algebraic manipulation, it's like you are dealing with two copies of the same system in the way that I describe later. Okay? So this is the reason why I will keep going in the future lecture, starting from today, with this notation Z and Z bar. You might wonder, what Z bar is just Z star? Why is using this? No, I'm thinking really as independent quantities, and at the very end, when I want to talk about easy model in the plane, so some very concrete physical system, at that point I have to do this identification. But until then, I'm free to do that. Okay. So that being said, therefore I have Z and Z bar variable, and I would like to encode this kind of transformation into an algebra. Namely, if I'm going to apply to a function, set of functions, how this transformation is going to act. So the way of doing is, imagine to do some infinitesimal transformations. And infinitesimal, here I choose to be minus Zn plus 1 times some epsilon, let's say. But this is you see, I'm essentially picking up one of the direction in which I can move my stuff. And therefore, I will introduce an operator ln made like this. Okay? As well as I will introduce another operator, L bar, with the index n, in this way. Now, when you act on function, so these objects are meant to acting on function, so you can immediately see that the commutator of two of them is also an object of the same type. The commutator of L bar, Lm bar is an object of the same type as before, and you express that these guys do not know each other, putting the commutator between them to be 0. Okay? Is clear how I derive this relation?
Can you please specify once again which algebra you're trying to do?
Yeah.
Because it was not very clear in this information.
Yeah. So imagine that. Imagine you have a function, let's say, of z. Okay? So a function of z. And then I submit z to a transformation z prime. So this will be z prime. But z prime is this. So the first order, this is gz plus epsilon dz over g. So the action, if I transform z to something else, I can see as how my function infinitesimally transform. Okay? So the action on a set of function of infinitesimal analytic transformation I associated to this. So epsilon n is any of these power law things. And therefore, you see that if you do minus z n plus 1 dz acting on minus zm plus 1 dz function, and you do the reverse, minus, at the end of the day, you see that will be equivalent to act like this. Clear to everybody? Clear or not? So, from this point of view, we encounter for the first time in this treatment, in this theory, the fact that we are dealing with an infinite dimensional algebra. Because the number of generators here goes between minus infinity plus infinity. Okay? So I have an infinite number of generators to deal with. Now, I have the same story with L bar. Therefore, as I said, my fields, physical fields, so my order parameters that originally and physically will depend on two coordinates, x and y. I told you I'm thinking that will depend on z and z bar. So they will have a certain property, this field, if I transform the z part only, or the z bar only. Although, I stress again, at the end of the day, this guy has to be physical field, so at the end I have to identify something. But we will see that we will concern with eigenvalues of these two algebras, and therefore you might wonder how the physical quantities, which are anomalous dimension and spin associated to the operator, are related to the this two splitting of the algebras. So the thing is, if you combine the two algebra in a symmetric way, so ln plus ln bar, so the same n, and in particular L0 plus L0 bar, the eigenvalues of this guy will correspond to the anomalous dimension of the field. On the other hand, L0 minus L0 bar, this will correspond to the spin of the field. Okay? So keep it so far as a bookkeeping. You will see later when we combine the stuff that putting together the eigenvalues symmetric combination add will provide for us the final physical anomalous dimension of the fields. The difference will tell us what is the spin of the fields. So the logic is I will diagonalize separately these two algebra and then I will combine together. Okay, this is the logic. And I'm anticipating that the sum will correspond to the physical anomalous dimension, the difference to the spin. Okay. Now, among this infinite number of operators, can I identify those which correspond to Möbius? Because after all, Möbius is a spatial analytic transformation, okay? So how shall I identify this? I shall identify the generator of Möbius as the one which gives rise to a field, to a vector field, because this object, apply, say, on the Riemann sphere, keep you moving the function. Is moving the function, is shifting. So this flow, this vector field, has to be regular everywhere. Okay? This is what Riemann, in Riemann mapping is, alias Möbius. So I have to identify which of these operators has this property. And the things is very easy. So I have the vector field, which I can associate to these things. And you ask, for which, sorry, here I have some coefficient, AM. Which are the coefficient AM which make me this field regular at the origin? In order to be regular at the origin, I have to kill all them less than -1. Okay? So, field regular at the origin implies that M has to be larger or equal than -1. Okay? So
Can you repeat this argument of regularity of the origin? Like, I didn't understand the answer.
thing is, Möbius are the only transformation which leave your sphere perfect as it was. So it has to be a vector field which move you along the sphere without doing anything, without introduce any extra singularity. Okay? So, in terms of this generator, I can construct a vector field. This vector field making linear combination of all these actions. In particular, choosing a particular map, I want to be regular in the origin. I can shift the origin wherever I want, but the origin at least in this parameterization. If you don't like the origin, I have just to do z minus z0 m plus 1 dz and asking regularity to a generic z0 point. If you want, this is what I'm doing. Okay? I choose the origin as 1 point. So if I want regularity of this vector field around any point of this sphere, the generator I had to employ has to be those with m larger or equal to -1. Now, the only subtle thing is, of course, the point at infinity, because you say, wow, okay, so you make now regular fields at any finite point of the sphere, but what about the infinity? And the trick is very simple. You change chart, you change mapping, and how I can go around the infinity with the map 1 over, which is allowed. Okay? So if I want to have regularity of this vector field also around the infinity, the thing I have to do is z, first of all, I'm mapping 1 over omega. And since this is a vector, in order to go around the infinity, I have the Jacobian. So this guy transforms dz over d omega times d over d omega, right? So the vector field around the infinity will be an minus 1 omega m minus 1 d over d omega. And then I've lost some power here with respect to the previous one because there is this Jacobian. Okay? You have to do this calculation. It's simple, but do it. So at the end of the day, if I want now this vector field to be also regular at infinity, the condition is that the m I have to employ are less than -1. So, summary. The only field which is regular everywhere is made by L0 and L plus -1. Okay? Now, you can see immediately what is the action of these guys. L0 will be the operator associated to the dilatation. You see why? Because here? No. This is precisely, I choose this crazy minus sign here. I think I did right. But unless you prove I'm wrong, this is it. Huh? They do not commute with themselves. No, they do not. This is what is written there. Applying two of them, you get a third one. Huh? They commute. There's minus. Sorry. Yeah, sorry. Now I understand what you meant. Yeah, sorry. You're right. Thanks a lot. Yeah, minus, yeah, sorry. No, and this explains why I choose this crazy minus Zn to do the right things with otherwise I have to swap M with N, and this is a big problem. Yeah, thank you, yeah. Okay, so, look, L0, so what I'm saying is among the infinite set of operators, there are three of them which has the following properties. First of all, they close a subalgebra. Okay? So let me do it here. So you see I have this algebra. So if I choose n and m to belong either 0, plus and minus 1, this will be a subalgebra, because L1, L minus 1 is twice L0. L0, L plus and minus 1 will be minus plus L plus 1. Okay? So they are a subalgebra. They close among themselves. Moreover, you can ask yourself, what is the meaning of L0, L1, and L minus 1? Now, claim L0 is the generator associated to dilatation. Why so? Because you see the L0 action is minus Z dZ. So it's like you are taking Z and infinitesimally you are doing 1 plus lambda Z. So if you apply this transformation to a function, this is the operator which implements the dilatation. Clear? On the other hand, if I take L minus 1 is simply the derivative. Just take my definition. Therefore, an operator which is associated to the derivative is just translation. Okay? So this is simple dilatation. This is simple translation. Less simple is L1. What is L1? L1 is minus Z squared dZ. This requires a little bit of work. You have to sit down, think a little bit what's going on. This implemented a spatial transformation in which you first invert, translate it, and you swap back again. Okay? I'm not saying it's simple, but this is what it is. So if you do it, you realize this L1 is indeed realizing this extra transformation which enlarges the original transformation of the conformal group. But is allowed and is one which kept the Riemann sphere into Riemann sphere. Yeah.
So if we didn't know about the previous transformations, we would have proven that, I mean, among the infinite many parameters, we just have three relevant. So we have
Three
relevant parameters.
No, don't use relevant. It's not.
Sorry, I mean three parameters
three spatial operators. These spatial operators are selected out to be subalgebra themselves. Some of them you clearly identify what they are doing. So dilatation and translation, it's obvious, it's under your eyes. What is unclear is this one. But once you realize they are closing an algebra, you can figure out what they are doing.
So is this enough equivalent to proving that the Möbius transformations are the only ones?
Yeah, in a way, yes, indeed. If you integrate infinitesimally these things, you get the Möbius. Yeah. So, indeed, the Möbius you can find, I will tell you later, as a solution of a differential equation. If you didn't know before, you will find solving this differential equation, which is nothing else, saying what are the finite transformations associated to this keep going transformation of this type. Yeah, so we know the answer. The finite one will be there. Infinitesimal, what you have to do? Well, you have to do A very, very small, B very, very small, C 0, and D whatever is a normalization overall. Okay? So this will correspond to these things here. So I want to say that this is the spatial one. Now notice, I'm anticipating that this is completely classical. So the only thing I realize is I have a space of transformation which is infinitely dimensional, complex function. I want to encode my knowledge in an algebra because I'm an algebraic man and I know how to deal with algebra. And this is where you end up. Now, what happened at the quantum level is that you have to add here something else. And this will become the anomaly I was telling you yesterday. So the theory is not symmetry, is not a symmetric things. There is an anomaly. And this show up adding an extra term to this algebra compatible with the structure that you have. So this term is not arbitrary. It's very strongly constrained what has to be up to a coefficient. So this is called central extension of an algebra, technically speaking. But we will see as indeed an anomaly of our conformal transformation implemented not on function but on quantum fields. This is the point. The point is, so far I'm using this transformation acting on functions. Later I would like to act on fields, quantum fields, which has their own singularity, their own structure of composition, and in order to do that, I need necessarily to enlarge these kind of things. With the nice things that when I go and check, I'm anticipating what this term will be if I put n and m 0 and plus and minus 1 will be 0. Simply because L0 and L1 and minus 1 are symmetry of my theory, and therefore should not spoil anything. Clear? This is the logic. Symmetry are preserved. Symmetry. So symmetry means L0, L0, plus and minus 1. All the other will be anomalous in a way or another. So when I will enlarge my algebra, I will have some extra term here that will be present for all the n and m, but n and m equal 0 and plus and minus 1. So this will be the things. Okay, so this somehow set the stage of the story. So it's like when you have to teach mechanics. First you do the kinematic part, you make all the definition, you make all you want to compute it, but then you have to do Newton's law. You have to do dynamics, okay? It's included in the story because the things are complex. Complex means you have an angle. It's not real. Yeah. So if I do a transformation which goes like e I theta, which is allowed, I'm rotating. Yeah, thanks for the question, but this is what it is. The key point is that you have complex number. So there are modulus, stretching, and angle, rotation. Yeah. Okay, so dynamics. Dynamics now, we enter into the real heart of the story. So, as Newton has to make some hypothesis. To proceed further, you have to make some commitment. Okay? So, for instance, he has to define the mass, what it is a mass, for instance, how these are related to how you are pushing. So, there are certain assumptions, I want to say. So, the assumption we are going to use is that from the experimental data that our friend in the lab provide us, we know that nearby the fixed point we have power law divergences. Okay? It could have been differently. A function which diverges, you can invent the most strange things. But for critical phenomena, power law seems the one that is selected out. Given that, we have to implement this, and I show you how the critical exponents are related to the anomalous dimension of the fields. This was the lecture number 1. So with all this knowledge, as a theoretical physicist, one say, my dynamics will consist of scaling fields, which are those that if I rescaling they will transform like this. Okay? Definition, scaling. So this is a definition. What is not a definition, what is a commitment, is that nearby any fixed point there will be enough, essentially infinite, number of scaling fields, and moreover they form a basis. So this is a strong commitment. Means that any fields you like, let me denote it here, psi, is not a fermion, no? It's any fields. In any point of the space, I can expand in terms of my scaling fields. It's an hypothesis, it's a commitment. What does means this? Means the following, that any times in any correlation function you are computing, it happens that you met psi, you are allowed to substitute this with these things. Okay? So the fact is a basis means that any other crazy things you are considering, you can always substitute within correlation function. Now here there is a subtleties on which I don't want to enter. The subtleties is weak identity and strong identity. And even in standard field theory can give rise to contradiction. Please read the book of quantum field theory. What I mean is, you might take this as a real position, which is an identity as it is, operatorial identity. This can be false. What happens is that it holds only in correlation functions. It's subtleties, I agree, but please do not ask, otherwise we open a Pandora box here. So, if you are curious, go to standard book of field theory, you realize what the point is. But for what we are concerned, it's enough that I can always substitute any fields with its expansion on a scaling field in correlation function. Okay? Say differently, we have to focus our attention only on scaling field. This is the message. Forget all the other. No matter how complicated, if I can express in terms of scaling field, let's understand how the scaling fields are. So this is the first assumption. There is another very strong assumption, which is the key point of all the story. The key point of all the story is this. What happens if I take now two fields I call A x and B y, so they are here. And then you say, well, x and y can be far apart, 1 kilometers. A live here in Arcetri, B is in Santa Croce. Yeah, but remember we are at the critical point. At the critical point, any separation, let's call D, I can stretch the length I like, but 0. Okay, I cannot bring to 0, but I can, any length D, I can map. This is a symmetry of the theory. It's a symmetry, so I'm allowed to do it. So if these guys were kilometer apart, with a transformation, which is a symmetry of my theory, I can claim to be Armstrong apart. Okay? It's a symmetry. It's not, I'm not violating anything. For what the theory is concerned, kilometer or Armstrong doesn't make any difference. As far as I don't put lambda equals 0. So it has to be finite. I can shrink, but not put to 0. So all this to say that no matter how x is different from y, I can consider that x is very, 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 very close to y. So from this point of view, these 2 points are really one nearby the other. And what about the guy in front there? Can you distinguish these 2 points? No. Unless you have an eagle eye. So this means this B local object under any purpose should behave as a local object. Okay? So this guy is essential local. And therefore, since I have a basis, whatever operator is here, let's say x plus y half, just to be fair with both of the 2 points. So this is essentially equivalent to have something which live here. Means that whenever I found this expression in any correlation function, I can substitute what is on the left-hand side. Okay? Now, that being said, let's specialize this concept. So far, you have not to even take seriously what I wrote. Just is important the concept. The concept is 2 B local objects under any practical and theoretical purpose is essentially local objects. Okay? Let's specialize this concept where A, B are the basis. So this means that I take Cn x, Cm y, and whatever I have to be there will be a field that I expand in the basis. So this has to be equal to some object like this, with some coefficients, which at this stage are function. Okay? Now, all conformal field theory story is in this relation that I will, yeah.
Psi or phi, like on the left-hand side. Should it be psi or phi? Are these the basis or any vector?
No. This is the these fields, the basis, phi n. Phi is the same object which constitute the basis of my scaling field. I'm just saying this has to be valid for any fields. It's a relation that has to be true for the foundation of my theory. Okay?
Sounds a bit confusing, this, right? Okay, sure.
Confusing in what sense?
We are are we respecting the orthogonality of the basis functions? I mean,
This will come later.
okay.
The basis might be even non-orthogonal. I mean, a basis is a basis. You do not need to be orthogonal. Okay? So let me repeat it. This is crucial. If you understand this, you have done. If you understand this concept, the rest is chemistry, as Pauli would say. Okay? But this is crucial. The crucial thing is, I repeat it, the crucial thing is we have a symmetry which allows us to rescale any distance in any stretch distance I want it. It's a symmetry, so I'm allowed to do it. Okay? Second things, I have a basis. Okay. Then let's come here. I take two local fields, arbitrary, and then I conclude, just by this symmetry, that this B locality is a fake thing, because I can shrink the difference x and y as small as I like it. So this object behaves under any purposes as a local object. Local object means localized somewhere. Now, if you want to be fair to both of them, you say it's localized in the middle. You will see that I will be unfair to the theory later, but for the time being, let me like this. Okay? So, the things I'm saying is B local object correspond to a local one as far as you computed in this coordinate, eta, to the point theta. Clear? This is the key point of the story. I can see some faces which are a bit disturbed. Clear or unclear?
Doesn't this mean that all the operators are the same? Because
No.
actually zoom in, and then I have two points which are very far from each other, and I say that the product of them is some point.
No, I mean, the operators are completely different. It's not the same operator.
Because it's kind of arbitrary that I take the arithmetic average of these points.
Yeah, indeed. You will see that at the end of the day I will place these things in Y. And the reason is, let me just use this, otherwise you will get confused also my later notation. The reason is x plus y half, I can always write down f plus some displacement, whatever it is an algebra here. But to get this displacement, I can go from here to there by derivative. But derivative is a field of my theory. So without any losing of generality, I can think that the field that lives on the other side is localized to y. Okay?
So maybe the practical question is, how is C related to A and B? How do you choose C in this relation?
You do not choose. This is dynamical things.
How is it related to A and B?
I'm telling you in a minute. I'm just saying that this B local object, to all matter, is a local object. Now, you should know how to compute it. But it's a local object. This is the only thing I'm saying. Then you can ask, how the hell, given two fields, I computed this other one? This I'm going. At the moment is, these two objects, the B locality is fake one.
Okay, and further down, give some insight on how to make this relation with it. So you are saying that for the basis, like vectors, this is the relation that holds.
Yeah. Now, let me go.
When we move x close to epsilon, we're assuming that the product of A and B has no problems in.
No, wait. I'm just read it as it is. This is, I told you, is not an equation. Is the concept. It's not an equation, it's a concept. The concept is B local is equal local. Here I left out a lot of stuff. And then now I'm telling you what is this stuff. Now. Okay? So at this stage, this has to be local. Next point, say, by the way, among the local fields I have my scaling field. Better than them. So let me stuck into this idea I'm pushing, the fact that I want to control what happened to two scaling fields when they are going one nearby the other. Whatever will be here, I just told you, can be expanded in terms of the same basis. So whatever should be here has to be written as an infinite sum which involve the same field, with coefficients which are highly non-trivial. And all the rest of our lecture will be how the hell I compute these coefficients. Okay? So this is the dynamics. So something is the idea, and something is then what you have to really compute to make the story up. So the idea is from symmetry and completeness of the basis, I got this relation. Okay? Now, when you compose two objects of one set and you get as a result an object of the same set, you have in mathematics what is called algebra. Okay? Algebra is any composition which take two objects and the result is a guy of the same object. You can get as algebra commutators, you can get plus, you can get, the operation depends. But the concept is each time you have an operation, here left unknown what it is, but you compose two objects according to certain rule and you get an object of the same type, you get an algebra. So this expression is called operator product expansion algebra. Okay? Technically is OPE. You will find reading paper of conformal field theory, people always refer OPE, operator product expansion. Okay? So this is at the level of how you compose, say, representation of spin. You get me two spins of SU2, spin 1/2 and spin 3/2, and you decompose in terms of spin, which are objects of the same type. In that context, this will be called Clebsch-Gordon. Okay? Is how you are splitting two representations. This will be representation of that algebra in terms of representation of the same algebra. Okay? Now, here the story is complicated because there are coordinate dependence. When you decompose SU2, you have never coordinate. You say spin 1/2 cross spin 1/2 is equal 0 plus 1. There is no coordinate. Here the complicancy is that our representation depends on X, on our space. The algebra is acting on this space. But if you forget this technical detail, the concept is very clear. You have an object which is an algebra. They will have representations, as usual. And then you are asking, if I combine two of these representations, how I decompose in terms of the third one? This is the things we are doing. Okay? Guys, will be no breaking, because we have no time, unless you are really dying. Someone, I will keep going. Is there any, because I can see him is watching constantly the watch. You want to go? Yeah. No, unless there is urgency to go, because we have no time. If you want to know how the story goes, we have no time. Shall I go? you can have?
Non-zero delta.
What is delta?
In the scaling operator, right? When you
Yeah.
phi lambda x
Yeah.
goes to lambda to the minus.
These are the eigenvalues of the spectrum.
But this shouldn't matter for the dynamics.
Will butter in a minute, immediately. So indeed, given that, so this relation, I just write using the logic I told you. B local is equal local. I have a basis for all the local, therefore I have an algebra. The interesting question is, can I get some information what this term is about? Answer, yes, we can get a lot of information. For instance, translations invariance. This automatically implies that these functions cannot depend separately by x and y, but should depend on the modulus. First consequences. Secondly, scaling. If now I apply x go to lambda x, y go to lambda y, given precisely that the fields goes like lambda minus delta n and m, this function necessarily has to be scaling function of weight delta n plus delta m minus delta kappa, up to a coefficient which I call, with a great fantasy, CNM kappa. Okay? So I'm saying from the very beginning, the only thing I knew was that this has to be true, up to some objects, which has to be function which carry the dependence on x and y. But I immediately realized that I have enough information to pin down what this function has to be. Has to be function of the differences, alias of the translation invariance separation, but not only, has to be functions which is homogeneous of weight delta n plus delta m minus delta kappa, up to a coefficient which I'm not able to fix. So this coefficient, these are pure numbers. These pure numbers, together with delta, are the dynamical data of the theory that we have to compute. So this is dynamics and not kinematic any longer. Kinematics, I put down all the stage of my things, what I have to do, how is things going. So what I'm saying is, let me summarize the things. I can summarize in the following statements. I have basis of scaling field associated to their scaling dimension delta. I have a composition of them which end up in numbers. Like this. And I'm saying any conformal field theory is solved as far as you give me all the spectrum of the anomalous dimension and all these structure constant, as they are called. Reason for that? The reason is, remember that I say a field theory is solved as far as you know how to compute a generic correlation function of your theory, right? Any. If you have this data, you can do it. Why? because any fields I will expand in terms of this. Okay? So any correlation function of any fields is essentially related to correlation function of scaling operator. But any n point correlation function scaling operator, I can always reduce systematically, one by one, getting down. So this means that from this I fuse two fields and I get something less. I fuse two fields and I get something less. And at the end of the day, I get just 1 point function. And in the meantime, I collect a bunch of structure constants along the way.
In your analogy with dynamics, what is the force? What is causing the motion? Like
It's an analogy.
okay.
Where are you from translational invariance? Should those be the...
Guys, translation invariant was my basic principle.
No, I know, but what you would, should it be the C with the hat? It's still the function, right? It's not the numbers.
It's a function.
It's the function, okay.
Yeah. So no, indeed. So at this stage, sorry, this I swap notation probably I was not clear. Let me then C hat this function. So as a function x and y can only depend on differences. For matching the scaling left and right has to be scaling function like this. So the only thing I cannot pin down are coefficients, which I call C and M kappa, just not making a proliferation of notation. Okay.
So we didn't use any conformal.
Not yet. We have just used the symmetry. Yeah, you're right.
Additional one we found out the
No. So far, no. You're right. You are completely right. So far, I have capitalized the most I have over symmetry, not even the inversion, if you want. The inversion was, if I want, you will see later how I'm going to use it, but you're right. I'm just using translation and scaling. And rotation, as I said, in complex number, and now the point is, if I want to compute these numbers here, then I have to make heavily use of the conformal symmetry of breaking the array off. So here, when I mean dynamics, just to clarify the analogies before, so one, in Newton you need the forces to compute something and then you have to solve the dynamics. Here dynamics means at this stage I encoded all I have in terms of symmetry and the best of my knowledge. But you see, I left out what? I left out all the symbol I use, alias what are the values. So what are the values of this coefficient? Boo, at this level are unknown. What are the values of this delta? Boo, they are unknown. Okay? So indeed, at the end of the day, the story is I will classify the reducible classification of that algebra, proper quantum. Out of it, I get irreducible representation whose eigenvalues are the delta. And out of it, from the composition of them, I get the structure constant. So if you want, the logic is like you study SU2, you study representation theory of groups. So you have a group, in this case we have an algebra. The completeness is that it's an infinite dimensional algebra. But imagine you have SU2 algebra. What you do with that? You classify the reducible representation. And you know they are classified by spin. So if you give me spin 5/2, I know that is an irreducible representation. The analogy is that this spin 5/2, 3/2, whatever it is for SU2, here the role is played by delta. Okay? So delta will be the irreducible representation which label them according to the algebra. But the idea is the same. What are C? The equivalent of Glebsch-Gordon when you compose spin. Okay? This is the analogy. The analogy is perfect. The only difference, which is substantial, as you will see later, is that, first of all, I'm dealing with infinite algebra and not SU2, which has 3 generators. And secondly, I'm dealing with something which is point-wise dependent. Spin, no notion of dependence in X. Okay? So there are strong analogy, but also differences. The analogies is any conformal field theory means when you classify you want to classify the phase transition. The amazing deep result is that all different manifestation in nature of phase transition is nothing else than different representation of this algebra. Is at the same level like if I come to you with a bunch of 21 function, and then I say, look, if you rotate them, look how crazy they mixed up. I'm talking about harmonic sphere. So I say, okay, crazy, fascinating this. No, behind there are all the SU2. So if you think a minute, all the complicancies of SU2 is not in the algebra. The algebra is always the same, 3 generators. The complicancies and the richness from atoms, spin and this and that come because you are using different representations. Irreducible representation in a group means there is a bunch of stuff that under the transformation they mixed wildly themselves. Okay? Here is the same. Any different class of universality will be different realization but of the same algebra. That will be that one. It's a deep conceptual point, absolutely deep conceptual. So this means that Ising or Potts model or ON model or any other crazy model, deep down, they do not differ each other very much. They are always associated to a common object. Okay? It's the representation which is different. It's the bunch of delta, it's the bunch of operators, it's the bunch of structure constants which are different as much as it happened in SU2. Okay? Is clear, the concept? So this is net and clear. The devil, of course, is in the details, which, of course, here you realize has to be more complicated because it's an infinite algebra, the representation has to be a little bit different, and we will see what it's about. But conceptually, it's nothing else and nothing more. An algebra and irreducible representation thereof, therefore associating to eigenvalues and associated to composition of representation. Okay? Clear? This is the theory is just what I said. To compute these ones, we have to do something. At this stage, it's not free. I cannot say what they are. Okay, so let's move on, because I want to now start building up the representation. Now, you have to have clear in mind how group theory works. If you have this, it's really everything is net and clear. What you do in SU2, I take as an example SU2. So the representation of SU2, so let me just spend just few words on this, because this is crucial at the conceptual point. So imagine that you have an algebra which is typically is right? Usually for a group you have something like this. So for SU2 you have 3 generators, that is S1 Sj is equal blah blah blah, and I equal 1, 2, and 3. So what you do with this? First, you choose one operator that you declare in any representation will take the representation diagonal. You can choose any of them, but you have to make a commitment. So usually you do SZ. So you are classifying SU2 by representation, which means matrices. In this case, the matrices will be finite, in which SZ will be fully diagonal. Okay? So your space representation means you have to give me vectors. The vectors will be classified by the eigenvalues of one of them, one of many of them. So usually you diagonalize SZ. In our case, we are going to choose L0 as the operator we are going to diagonalize. And indeed, since L0 is the dilatation operator, the delta will be eigenvalues of L0. Clear? So the equivalent of SZ for SU2 there will be played by L0. So in any representation, I'm diagonalizing L0. The eigenvalues will be delta, delta I, delta 2, delta 3, delta, all the delta. Now, that being given, what they do the other? In SU2, what you do, you make linear combination, and you end up, which are allowed, because it's, and then you get S plus and S minus operators. When you go and compute what is the action with help of these things, you realized that you have something like this. When the commutator of one operator is proportional to the other one, what it does acting on our eigenvalues of this is that will shift the values of these things by the proportional term which is here. So in SU2, using S plus and S minus, if you have any vector associated to a values S hat 0, you can move upper by S plus, or you can move down applying S minus. Okay? So when you have an irreducible representation of SU2, when you start from some vector, you end up you end up to the upper one, in which you have a limit. You know, in that case, you cannot overcome something. And the last vector will be annihilated by S plus. Vice versa, if you start from something, you go down, 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 you arrive to the latter one, which will be annihilated by S minus. So, from what I'm saying is, you understand that there are vectors which are more equal than the others. In SU2 is either the vector you start from the bottom, or the vector you start from the upper. Okay? So let me choose as a basic vector the lowest one. So this is called highest weight vectors. Means once you give me this vector, I can construct for you freely the reducible representation, keep acting with S plus. And then once I collect all these vectors along the way, this is the reducible representation. Okay? So these are concepts of group theory. So group theory means you have to build up a vector space, because at the end you want matrices for this operator acting on a vector space. So you have to build up this vector space. How you do it? You do it choosing the highest weight vector and keep acting with all the rest of operators. Okay? So you see immediately, from this point of view, I didn't tell you what is the term on the left-hand side, but at this point, let's at least talk something concretely. So at the level of quantum level, the algebra we are dealing with will be called Virasoro algebra. Will be this. Okay? So I have to find irreducible representation. I have to find irreducible representation of this algebra. I will derive this term. I'm just saying, I'm anticipating this will be the algebra to deal with. So imagine I repeat the story of SU2, alias I choose L0 as the eigenvalues which is diagonal in any irreducible representation. And let's compute what happened with Ln. You see that this is the algebra. Okay? So you immediately realized that if you act on a vector eigenvalues of L0 with Ln, this will shift the eigenvalues of L0 by minus n. Clear, everybody? So imagine you have a vector that this is delta delta. Okay? And now imagine that you act on Ln here. Okay? And you want to know what kind of object is this Ln applied to delta. So what you do is, sorry, I have to invert the story. You have a delta which is defined the way I say it. So L0 is equal delta delta. And now you want to know what is Ln applied to delta. So you want to know which kind of vector is this. I claim that this object will be a vector, eigenvector of L0, but eigenvalues delta minus n. And the reason is that if I apply L0 here, I will have commutator ln L0 plus the commutator which is minus ln applied to this. Okay? So this one will provide me delta minus n ln delta. So from which you understand that this vector is eigenvalues of L0, but the eigenvalues has been shifted by minus n. Okay? Now n can be plus and minus. So what happened drastically different from SU2 is that while in SU2 the range of values up to which I can get is finite, here I have infinite number of operators that I can span arbitrarily high. Okay? So this is the main difference. It's kind of a nested, infinitely nested SU2 algebra.
So there's no fixed step in the sense.
Above not, below yes. So for that reason I say I choose in the analogy with SU2 to build up my irreducible representation starting from the lowest eigenvector. Because in SU2 you say my highest vector is the one annihilated by this guy. So this identify uniquely this object once you give me the dimension. The rest of representation is acting with this all possible combination of the other one to this. Okay? In our case, what we will do is we define this object to be eigenvalues of this for all the n bigger equal 0. So this condition is the equivalent of highest weight vector for SU2. And the rest of representation will be built acting on delta with all the possible L minus n, all the negative one. And the representation will be pictorially like this. So something which extends infinitely high. I will be more detailed later. I'm just telling you to give the flavor what's going on. The flavor is an algebra, very interesting algebra, which is kind of nested SU2. But the building block at the level of idea is always the same. You create an irreducible representation on an algebra, identify the highest weight vector, and acting with all the rest of them. Okay? This is the idea. Here is the same.
I don't think we use the analogy, because in that case we had a lowest eigenvector annihilated by S minus, but then we act with S plus to
Yeah.
get the others. In this case, I see we're acting with Ln to get the others.
No, L minus n.
Do we just prove that Ln does?
I have L minus 100, L minus 1 milliard, L minus 3 milliard. So all the positive annihilate the highest weight state. All the negative build me the representation. Okay? This is the point. So this means that once I use this one, I have not the problem of getting arbitrary down. Arbitrary down means something drastically for physics. You might ask, why the hell I'm doing this and not do the vice versa? No, guys, because delta is how the correlation function goes. Remember that you have scaling fields like that, which actually we'll prove in a minute, which goes something like this. Okay? Now, delta positive for physics is okay, because correlation has to decay. But if you give me delta negative, arbitrary negative, you have the crazy situation that field get more and more and more correlated when you separate them. No, it doesn't work. Clear? It's clear the idea why I have to build up physical example employing this, because I have to avoid the most I can negative eigenvalues. Because negative eigenvalues in this theory means increasing correlation, not decreasing. And in any physical theory, you should have cluster. How to say, when you separate object, the things has to decouple each other, not they become more and more coupled.
As far as I understood, we have like infinite amount of different deltas, right?
Sure. Well, the number of delta can be finite, the number of delta, but the number of vector that you build up on any delta will be infinite.
Okay, so like I can use them as a different seeds for different representations.
Exactly, exactly.
Can I understand?
Yeah, this will be detail weight. This will be all the theories about how these representations are building up, how they interact, how they decompose, and so on and so forth.
How do you get this Virasoro algebra emerge from the algebra we had before?
No, I said I will derive it. I just say for the sake of completing this kind of discussion, what the kind of animals I'm dealing with, I just introduced the extra term. I just introduced. At this level I didn't justify, but I will justify completely how this will emerge. Okay? So let me just make a summary of this, because this is the crucial conceptual point. The rest is really, as I said, is chemistry, namely you have to just do the things. So the basic thing is we have scaling field. Scaling field fulfill this operator product expansion. This product expansion is based on two objects at this stage unknown, which are what are the set of delta and what are the set of C. So these are the dynamical data I have to compute it. To compute, I have to set up and to understand what they are based on. And the meaning is the delta will be the irreducible representation of an object, which is an algebra, which is this one. It's called conformal or Virasoro algebra. It's an infinite dimensional algebra, and the irreducible representation of it will be labeled by the delta, labeled, because representation means bunch of vectors. So when you say spin 5/2, you have to think that there are many vectors, 11 vectors. Not 5/2 is just a label, the representation, but the space is 11 vectors. Okay? So delta parameterizes a reducible representation that will build up in terms of objects which are eigenvalues of L0, are annihilated by all the positive modes, and the rest of representation will be building up, acting on delta in all possible L minus n ways. And you understand how beautiful the mathematical problem can be, because there is a very interesting combinatorics. So the analogy is you have a building with many, many floors. Okay? because I just proved you that acting with ln, I'm shifting by integer delta. So delta can be any crazy numbers, but if I act with the ln, the new delta has to be integer separated by the other. So it's like you have a building where the 0 floor can be whatever height, but all the others has to be first floor, second floor, third floor. Now, if you want to reach fifth floor, you can enter in your lift and press 5. You arrive there. But you can make one floor, one floor, one floor, one floor, especially if there are other people that have to stop to the previous floor. But you can make 1, 2, 2. You can make 3, 2, 4, 1. Clear? So what I'm saying is, if this is the building, and you have to reach this floor, starting from here, you can go in one way. It will be L minus 5, my analogy. Or you can do like this, acting L minus 1 5 times. Or you can do L minus 3, L minus 2. Or you could have done L minus 2, L minus 3. So I want to say there is a beautiful combinatorics behind. This problem of combinatorics was solved by Ramanujan with Hardy. It's a famous problem of combinatorics. And the problem consists in this. I give you an integer number, 10. In how many possible ways you can decompose the number in lowest number such that the sum end up to 10? And the combinatorics is exponential. Immediately, you understand immediately because there is a recursive there. So if you have a certain number of way of going to the floor 10, and you ask how many ways I have to go to the number 11, first of all you have all the way up to 10 plus 1. Yeah, but then you open up all the previous stuff. So the number of ways of getting here, which in combinatorics is denoted Pn, is in how many possible ways you can split a number is sum of numbers lower. This will be the degeneracy of this level. And the degeneracy of this level grows typically exponential.
Is there something to do with Jung diagrams?
With?
Jung diagrams? No?
In this case, are not much help. No, I mean, I understand that the basic of your question, but in this case, to the best of my knowledge, has never been used because, as a matter of fact, it's much simpler, the things, although the quantity that you get is highly refined. But you do not have a technology like Jung diagram is not needed.
One question. Why do we define this highest vector for m more than 1? How do we know the minimal delta? Is it because we want to...
No. What I'm saying is delta, the spectrum of delta, is given by these things. So if you want to know which are the values of delta, essentially you have to diagonalize L0. So at this stage, delta is whatever. I didn't tell you what delta is. This is highly non-trivial question, what is the spectrum of L0. But what I'm saying is, if you give me eigenvalues of L0, name it delta, and this satisfies this condition for any delta. For any delta, satisfy this condition. So all the positive one annihilate these states. Once you give me vector which satisfy both of these conditions, leave it out what is the value. The things I'm saying is the algebra problem is finished in the sense that the irreducible representation built on that is obtaining, acting on delta in all possible way with the L negative modes.
Yeah, this is clear. I just didn't understand why this should be satisfied for all n bigger than 1. Why 1?
Because otherwise you bring down a delta minus 1. And no, once I have this, I can reapply once again L1. And I can apply once again L1. And so keep going, I will go to hell. No, you see, once you open the door, you have done. You have to shut the door and shut forever.
Because we cannot have negative.
No, I mean, something is mathematics, something is physics. I can tell you privately a joke, probably the students of SISSA knew already about Feynman, difference between physics and mathematics. Ask them. We are doing physics. So mathematics you can have. I mean, no problem. But physics-wise, you want correlation function of physical field to decay at infinity, not to grow at infinity.
How do I know that different products of ends are different? That is the general sense given by the combinatorics?
No, I mean, there is a problem of ordering. I will face later. Let me answer him because so what he's asking is how really construct the real degeneracies. The thing is like this. Imagine you want to go to the third floor, okay? You have L minus 3, L minus 1, L minus 2, L minus 2, L minus 1, right? The sum of all of these give 3, minus 3. Now, the question is, are these two guys really independent? And the answer is no. The answer is L minus 1, L minus 2, I can write down as L minus 2, L minus 1, plus commutator. Right? But commutator is L minus 3. So this means that this object is this plus L3. So I have to select out in all possible ways the ones which are independent. And the rule is very clear. The rule is you make a string of all the nn like this, such that the sum of ni is equal to the level you want to reach, but you give them an ordering. Either this or the other way, it doesn't matter. But you give an ordering. Because like this, if I use L minus 1, L minus 2, if I swap it, I have L minus 2, L minus 1, but this is linear dependent from the other one.
And how do I know that L minus 1, L minus 2 is linearly independent from the minus 2?
No, this is given. I mean, it's like you are asking how I know S1 is different from it. Yeah, I mean, this is not a loud question. Yeah.
The general official level, I need to sum up over all combinatorics and
Yeah.
over all seeds, which gives me the same.
Yeah, you have to count in how many ways you can reach them. There are different vectors. It's not the same vector. No, it's not the same vector.
I have this level which was generated by a need one seed from here, but for example, I also generated this level from another seed from other place, like from other delta is different.
No. No. Unless there are crazy resonances with the delta, namely two delta which differ by an integer, this never happen, or happen under very, very crazy circumstances. But unless they are in resonance, delta 1 is completely different from delta 2, physically. So you will have number like 1/16 and say 1/2. They never talk each other. There are two buildings set on different floors. So the height of the other never match, never. But the things you have to understand is not that at the level n you have a unique vector. We have many, many vectors, Pn as a matter of fact, given by all possible way of getting there. So they are different vectors. Okay? When you say in quantum mechanics this level is degenerate, means exist many states with the same energy. Not exist one state. Degenerate means there are many different that share the same energy. In this case, they share the same value of L0.
And why do we care about these combinatorics? Didn't we exclude the n larger than 1
I didn't get it.
So do you exclude the generators which don't belong to 0, 1, minus 2?
No, we do not. I mean, no. I didn't exclude it. No. I just said the beginning is I'm going to have an infinite number of generators. Some of them have a very specific meaning. And by the way, are those which implement symmetry.
So those are the only ones we use?
No, this is exactly the point of the story. This is the key point of the story. There are symmetry that provide certain information, like the operator pro expansions to be power law. These are information. But symmetry alone cannot provide me neither the spectrum nor the C. So I need to employ the other operators, even though they are not symmetry. So the variation of the action will not be 0. But I expressed this yesterday or wherever. Even though it's non-zero, so it's not a symmetry, as far as I know what is on the right-hand side, I'm fine. And this I will derive, okay? So I will employ the ln, even though they are not symmetry, because this will provide me a lot of information as far as I know how to control them. This is crucial, the story. The difference between symmetry and operators that are not symmetry, but you know what they do. Guys, once per time.
You're saying that if we consider
Capizzi.
if we consider L minus 1 and L minus 2, and then also L minus 2, L minus 1, that means overcounting there.
Overcounting.
But then in the example that you gave with the diagram, did you say we could do 3 then 2, but then also 2 then 3?
Indeed, yeah. Was before the question. Other question? Capizzi, what you have?
This is only a curiosity, okay? There is an explicit expression for the number of ways we can get n large as the sum of...
There is. Since you love number theory, don't you? No? I'm right? Not being shy. So there is this beautiful identity. So the function you are looking for, the degeneracy, you can get as far as you take this infinite product, you expand it, and then you collect all the power which end up to n. From this you get the combinatorics of the story. Now, this was derived by Hardy, Ramanujan, and this and that. For a physicist, this is a beautiful identity. SISSA students, shut up, because they know the answer. What is this identity for a statistical physicist? Partition function, but computed in two different ways. Right? Grand canonical versus canonical. Because you have a bunch of excitations that you can sum up independently, free theory. So if you do that, free theory, each of them bosons is one of them, and then being independent, you make the product. Partition function is a splitting. But I can do something different. I can take my excitation, combine a shell of energy n, multiply in how many ways I can have it, and sum all of them. So this will be the grand canonical partition function of free bosons. This is the microcanonical one.
So is the n greater or equal than 1 a constraint or what we should avoid? Sorry, I don't get it.
What do you mean avoid?
N should be greater or equal than 1.
Yeah.
What is the problem if n equals to minus 1, let's say?
No, L minus 1 act. L minus 1 act. I'm sorry that I drove you here. It was a mistake. But since you are asking, so this will save time later. So let's be very explicit what I'm doing. What I'm doing is, I want to construct a representation of that algebra. How you do it operatively. So you say, I have a vector which is eigenvector of L0. The value you cannot get from here, okay? It's a separate question. This bloody vector satisfies this condition. L1 delta is equal L2 delta is equal L3 delta is equal blah blah L1 millions delta equal 0. So it's an infinite number of constraints, this vector, are annihilated by all the others. Okay? All the positive one. And then you say, okay, now I have a vector which I pretend to know what it is. It satisfies infinite number of constraints. How I can build up a linear space that if I act in all possible generator remains always the same space. This is an irreducible representation. Answer, you have to construct this vector. Given delta, the first one you construct is L minus 1 delta. This is a new vector, so let me call this V0. This is, I call V1. It's a new vector. Now, this, in terms of L0, has eigenvalues delta plus 1.
Okay.
Then, is the only ones? No, because if I start doing L minus 1 square, there is no vector which they mixed up. So I have to add it. I have V2, which is L minus 1 square, but then I realize with dimension delta plus 2 is not the only vector. I have another one, L minus 2 delta. So this will be V2 1, and this will be another vector, V2 2. Are these completed irreducible representation? No. Because if I'm now acting on any of them by L minus 1, another one, what is the next one? I have to include another vector which is L minus 1 cube delta. Then I have to do L minus 1, L minus 2. This will be at the level 3. And then you keep going. So you build all the representation is associated to the arbitrary action of all the possible generators acting on them. This string is completely arbitrary as far as n1 is less than n2. I don't know how you choose it, yeah.
Okay, so basically a very simplified process for SU2 would be how we obtain the Gibbs-Gordon coefficients, right? Because
you are wrong. You obtain the representation. You don't get completed the things. You just construct the stuff. You're just knowing the coefficient, how they are expressed. Gibbs-Gordon is when you combine two. No, you are confusing terminology. What you are saying is, I get the coefficient of the vectors.
yes, okay, not combine, okay.
Not Gibbs-Gordon. Gibbs-Gordon is 1/2 cross 1/2 is equal 0 plus. So you want to know what, okay? Indeed, this level, this vector, these are linear space. I can multiply any coefficient I like it. So from this point of view, I don't care. You see? So in SU2, you care because you want, for your convenience, already the normalization of the states. But, I mean, if I left out this problem, is a vector.
How does this guarantee the positivity of delta here?
No, nothing.
Doesn't.
No,
It's
it doesn't.
Okay.
It's another story.
Okay.
It's another story, yeah. Okay? It's not guaranteed at all.
Okay.
This is just pure algebra. You can program on your computer without the computer know what you are doing. So, okay, this is the way how you build up an irreducible representation once you have generators. The rule is very simple. Generator is do all possible combination you can with the generators, starting from some vector that is uniquely identified. Okay, clear? Yeah.
Like in the comparison with SU2, in that case we have an upper bound probably because we want like the C component not to be bigger than the SU3.
Yeah.
We fix the bound. But is there an intuitive way to understand that there is no degeneracy? Like we cannot construct like a S2 plus something that brings us like two orders.
You mean in SU2? No, yeah, but in SU2 is simple because you climb along the representation acting only with one operator, S plus.
Yeah, because we can also construct something that is just two-step, that gives us the vector 2 steps higher.
No, you can go step to step, but at any level you can apply just a string S plus n times.
We cannot construct something else.
Yeah, there are only two well, in SU2 there is S0, SZ, which classify the things, so it doesn't do anything. Each time you apply to a vector, give you a number. And then there are S plus and S minus that make you climb either up or down. You have to decide how you want to climb this irreducible representation. In SU2 you have two equivalent ways. Either you start from the bottom and you climb with S plus, but then you cannot climb back. I mean, you have to go up always, or you do vice versa. Here, in this algebra, I'm saying the sanity things to do is to start from the bottom, because you want to avoid negative values for very good reason. And the representation is done applying all the rest of operators which make you climbing up, but then you have infinitely many. And they are independent. So this is why you have degeneracies. In SU2 you cannot have it. Or better, you probably are confused when you have a spin 0. For instance, spin 0 can come, make 1/2 cross 1/2. There is always a spin 0, SZ equals 0. But one belongs to the irreducible representation 0, and the other representation 1. I'm not talking these degeneracies, because this is a tensor product decomposition. I'm just take one individual things and doing it. Last question, then we go to lunch.
I didn't get one thing, but when constructing this kind of cone process of I guess it's of a 0, is there a way to reduce the degeneracy using some Casimir-like corridor?
No, not in this case. No, there aren't. For a very good reason. So. Okay, so have a nice weekend. We'll see you next week.